Hello, welcome to CE 3372, Lesson 7, and we're going to continue with our prior lessons where we built our own home-built solution tools for finding discharges and heads in pipeline networks to include adding pumps. And the methodology here would extend to other hydraulic elements that would make sense to add to a model, although beyond this you would want to be using professional software. So the hydraulic principles, we'll quickly review them. We'll quickly review constructing the network and then go add the pumps. Recall that branch and loop systems are called networks. There's multiple paths for water to flow. The external demands are applied at nodes. External supply, if necessary, is treated as a negative demand. The two major principles are that there's conservation of mass at a junction, where the inflows minus the outflows equals 0 at the node. Demand is considered an outflow. It's usually moved to the right-hand side of that balance equation and expressed as a positive number. The head at a node is a single value. It's often expressed as a pressure, but you can visualize it as the height of a column of water in a piezometer at the junction. We also apply conservation of energy or head loss along conduit using a modified Bernoulli's equation. It can include fitting losses if they're known, and there's one energy equation for each link. The analysis techniques are listed here: Hardy-Cross, Newton-Raphson, and the hybrid method, which is what we're using. And the hybrid method, continuity is written at nodes, energy loss or gain is written along lengths, and the gain is going to make sense in a second, and the entire set of equations is solved simultaneously. If we want to add pumps to our system, a pump is treated as a link that adds head in a predetermined flow direction rather than removing head. If we recall this picture, usually we have head loss in the direction of flow, but that link could instead be a pump, and instead of causing a head loss, it's going to cause a head gain in the direction of flow. And the major change is going to be how that equation is represented. So the pump replaces a link somewhere in the network model, and typical equation structure that we're using here is the added head of a pump is equal to its shutoff head minus some pump constant K multiplied by the flow rate Q raised to some exponent. We're going to use the prior lesson example as the network, and we'll replace the supply pipe with a pump and see how that changes the system of equations that needs to be solved. So here's our prior network, and the only change is that pipe 1 is now removed from this row and it's replaced with a pump. And if there's a need to have a pump and a pipe, it's a simple matter to add a couple of extra nodes into the system so that the pump can be connected in. Here I'm just taking a cop out for the sake of brevity. So our pump curve is H sub P is equal to some shutoff head minus KQ. In this case, I've chosen the exponent 2 squared. We want to specify how it would be represented. In our example, we're going to use a shutoff head of 104.54 feet, the pump constant of 0.25 feet per cubic foot per second squared, and the exponent is 2. And those are all can be changed to mimic the behavior of any practically available pump you might want to consider. The actual pump curve function, I choose to build it in a similar fashion as the loss terms. So the pump curve function has shutoff divided by the absolute value of Q minus K pump times the absolute value of Q, and the result of that operation, the subtraction of those two, is then multiplied by Q. This allows the function to keep track of direction, and we probably should test for the implicit divide by 0 that can occur at Q equals 0, but it might, and then if that occurs, we simply just use shutoff head and proceed. Okay, so here's how the equations would change from the original problem. So the original problem, recall that the connection from the supply reservoir into the system was through this pipe number 1, which is going to go away. The link is still going to be there, but it'll no longer be a pipe. And the head in our original one was 100, and we're now going to reset it to 0. Then we're going to insert our head function. The head function, I'm representing it as h divided by q. and it's the part of that pump curve function that doesn't include the discharge non-absoluted. So when you multiply H over Q times the actual value of Q, you get the added head of the pump. And it's going to replace the link 1 loss equation, or loss functional. And here's what the network analysis with a pump now looks like. Literally, we change this coefficient here. Naturally, it has its same behavior in the Jacobian matrix, and we replace this value here. And we have to provide the function capability to evaluate h of q at every value of q. So let's now go and take a look into our Excel model and see how to solve it. Okay, so this is the prior model with pipes 1 through 6, and then nodes 1 through 4. We've already obtained solutions, and what we really need to do now is make those two changes here. The big one is going to be this. And now instead of a loss function, this is going to be a pump function. So let's rename this pump. And we don't really need much of that material there, but we do need to have the, let's see, let's put some, we'll put some rows in right here. We need the shutoff head. Okay, H shutoff, and we need the pump constant. Our shutoff head was 104.54 feet, and our pump constant was 0.25, and we need the pump exponent. Insert another row. In pump exponent. Let me use these underscores, make it a little easier for me to read. And the shutoff head. Okay, so now we've set off that, and the big change is going to be how this term is represented. So instead of now being a pipe, it has become a pump. And the expression is, this is equal to the value of shutoff head divided by the current pump rate plus the pump constant, actually it's minus the pump constant, times the pumping rate. And we're going to play a trick. Since it's directly replacing, there's simply a sign change. There is our pump constant right now. Let's set you to play a sneaky trick here. And the other change we want to make is in the right-hand side. We want this to be a -0. And we've now changed it into our new problem. And with any luck, first thing I know is that the flow rate through the pump needs to be 8. And the resulting head at node 2 should be in excess of 100 feet if it's going to work at all. So let's go ahead and try and see what happens. So got the 8 pretty good. And lo and behold, we now have 88 feet of head at that node 2, 52, 53, and 51. And we have our f of x term is equal to 0. And so a very small change in our existing problem allows us to incorporate a pump. Pumps don't have length, diameter, roughness, gravity, viscosity, pi squareds, diameter to the 5th. So we could even get pretty here. Control Z. We can even get pretty here and highlight that to indicate that those are blank for the various don't need one of those. And there is our model. Very simple change to incorporate a pump into the model. Okay, let's go ahead and reset it to 0. And, oh, I didn't want to do that. Okay, that's what I wanted. I want to actually start it from the correct answer. Show you another powerful feature of either roll your own or commercial software. A special. If you've done a lot of simulations and you feel like you're close and it's stopped, it's relatively simply to restart at your last good value. And now when I run the simulation, it's not going to be very interesting because I'm pretty sure I'm not quite at 0 yet. Done. That was 60 iterations, and we now have the flow and the pressures in the system. Okay, that concludes this episode, lesson number 7.